Welcome back to another video with us here at LMDN STEM Academy. In this video, we will be working through the June 2023 past paper question. It's question 2 on dynamic equilibrium. A student placed a known quantity of frozen N2O4 in a sealed tube and allowed it to warm up to room temperature. As the vessel was warming, a brown gas appeared, which indicated that the frozen N2O4 had vaporized to form a gas and then decomposed to form NO2 gas, according to the reaction below. The student allowed the reaction to proceed further until equilibrium was reached. So here we have a dynamic equilibrium set up between N2O4 in the colorless phase and NO2, 2 moles of NO2, which is a brown gas. And we are given the delta H, or the enthalpy change for that equilibrium, which is positive 58.0 kilojoule per mole. So the first part of this question asks us to explain the term dynamic equilibrium. So dynamic equilibrium refers to the state in a closed system where molecules of reactants are continually being converted to products and molecules of products are continually being converted into reactants. In this state, the rates of the forward and backward reactions are equal and the concentration of reactants and products remain constant. Part 2 says state what is observed when dynamic equilibrium is reached in the reaction above. So here's our reaction. Initially, all we had was colorless N2O4, and as equilibrium is reached, we're gonna see this brown color appear, right? Which is indicative of NO2 now being present, right? So the color in the sealed tube goes from colorless to brown once dynamic equilibrium is reached. Part 3, state Le Chatelier's principle. Le Chatelier's principle states that if one or more factors that affect an equilibrium are changed, the position of the equilibrium shifts in the direction which opposes the change. Okay, so that's a statement of Le Chatelier's principle. Now, in part 4, write the expression for Kp, which is the equilibrium constant in terms of partial pressures for the reaction above. So since this is a gas phase reaction, we can in fact write our equilibrium constant in terms of partial pressures. And so here's what that would look like. Again, we're gonna have our product on top, so that's NO2 on top. And since there are 2 moles of it, we're gonna square its partial pressure, okay? So remember, Kp is written in terms of partial pressure, so that's what my P represents. And I'm squaring it for NO2 because I have 2 moles of NO2. And then on my denominator, I'm gonna have the partial pressure of my N2O4. And because I only have 1 mole of it, then I don't need to write any numbers there, okay? It's just 1. And so that's my expression for Kp for this particular reaction. So moving right along to part 5. Part 5 says, in the space provided below, draw a graph to show the concentration of N2O4 gas and NO2, how they are expected to change as the reaction proceeds towards equilibrium, okay? So here are the axes that we were provided with, concentration and time. So let's think about this graph now and what it should reflect. So when initially, right, the question told us that initially, all we had was N2O4. And so at a time equals 0, so right here, all I will have up here is my NO2. Right? So all I'll have up there is my N2O4 rather. I'm starting with N2O4. So I have only N2O4 at T is equal to 0. And I have no NO2. Okay, so all I have is N2O4. So NO2 is 0 and N2O4 has a value, right? Whatever that value was, they didn't tell us that, but we know that it exists at a particular concentration. So as time progresses, what's going to happen? N2O4's concentration is going to fall down as it gets converted into NO2, right? And what's going to happen to NO2 over time is that we had none initially, but as the N2O4 falls down and equilibrates out, in that same way, the NO2 is going to be raising its concentration until it levels out. Okay? So this curve here represents my NO2 gas and how its concentration changes over time. And then this shows how the N2O4 falls down over time and then finally equilibrates. So that's my N2O4 gas. That's what that curve there represents. And so at this point, right, where we see the leveling out of the concentration, we know that equilibrium is reached, okay? Leveling out, the concentrations are not changing anymore. And that's one of the key features of dynamic equilibrium that we spoke about earlier. Okay, the concentration of our product is constant and the concentration of our reactant is constant. So this is our equilibrium point of this curve, okay? Equilibrium concentrations, okay? So let's go forward, and in this particular question, we were asked to account for the shape. Now, while we were drawing the curve, we were accounting for that. So let's just say it here. Initially, at t is equal to 0, only N2O4 gas is present, only this is present, and no NO2 gas. As the reaction progresses, the concentration of N2O4 decreases as it decomposes and gets converted to NO2. The concentration then of N2O4 gradually decreases over time, and the concentration of NO2 gradually increases until both concentrations now finally level off or become constant when equilibrium is reached. And that's exactly what we showed on the previous question, okay? So moving right along to part 7. Yeah, part 7 says, state what is observed when the sealed tube is cooled to 0 degrees Celsius. Outline the reason for what is observed. So let's think about that a little bit. In the original question, right, they told us that equilibrium was attained at room temperature, right? So we'll have to start our discussion there. Equilibrium was attained at room temperature, and then the tube was which contained the equilibrium mixture was then cooled down to 0 degrees C. So there's a drop in the temperature that took place. So we'll start our discussion there. So since the equilibrium state was attained at room temperature, cooling the sealed tube to 0 degrees Celsius is going to disrupt the equilibrium, okay? In order to reestablish the equilibrium position has to shift in such a way to raise back the temperature of the equilibrium mixture. Remember, we started at room temp, which is about 25 degrees C. That's where equilibrium was established, and it dropped to 0, right? So we have to find a way back to room temperature in order to reestablish the equilibrium. We have to go back in temperature. And so since this reaction is exothermic in the backward direction, right? The forward direction is endothermic. We are told that here. So we know that the backward is exothermic. So since it's exothermic in the backward direction, then the equilibrium will shift to the left, thus using up NO2. Why will it shift to the left? It will shift to the left because that is exothermic in that direction, and we need to go in a direction that will allow us to raise back the temperature of the equilibrium mixture. We know that exothermic processes give off heat, and so that will enable us to raise back the temperature and reestablish equilibrium. When we go to the left, we are using up NO2, which is brown, right? And so then this is going to result in a disappearance of the brown color, and we're going to go back to colorless, which is what the color was initially, right? And so that's how we explain that. And again, that's based on the Chatelier's principle. It says that if you decrease the temperature, right, of an equilibrium system, the equilibrium will shift in the exothermic direction. So from a temperature standpoint, that's what Le Chatelier's principles says would happen. Okay, and so with that, we've come to the end of this question. Definitely give this video a like, subscribe to this channel, share this channel and this video with your classmates. Thank you for watching, and we will see you in the next video.